Everyone, welcome back to SAT Math Question of the Day with Professor Emeritus Seth Chaiken, University of Albany, and Joel, Seth's brother. We're here to hopefully show you how to approach SAT math questions, maybe even other types of math questions. Here we're doing Khan Academy practice. Khan Academy tells you what the 40 topics are that's on the post-2016 SAT. And there are 40 topics, and we are now going to hit the hardest questions in congruence and similarity. If this question you find too hard, then go back to Khan Academy and please do the other questions. There are 15 questions that are before this one. You see how we get 4 things here? That's where at the highest level, the 16th to 20th questions. Go back to the other questions and practice. In fact, even if you know how to do these problems, go back and practice so you make a ton of mistakes on your practice. Anyway, please try the problem, pause, and we'll come back and do it. So, given the lengths of the segments, what is n to the nearest 10th? So, basically you have to know the relationships. This is a geometry problem. We haven't done a lot of geometry. Seth, isn't it, you have so many ways to make the relationship, but isn't it 4.2 over n is 2.9 over 5.8? Is that what you were thinking about?
Thank you for writing the 9 so we can understand it. Yes.
You're very welcome.
However, since the goal is to calculate n, it is really wiser to put n in the numerator.
You're right. Now let's go back and post April 17th. We're always going to ask ourselves, is there a faster way? Is there a pattern or a faster way to get the answer? And there is a pattern between 2.9 and 5.8, right? So it should be easy to do the math. But is there a faster way?
Right.
Is there a faster way to have set this up? I don't know. I don't know if there really is. The problem is that if you don't know how to set up the proportion, you can't really do the problem, can you?
That's right.
Yeah, that's a problem there, right? So then you can see that it's 8.4, right? So what do you do if you don't know? Okay, the way I view geometry, a lot of geometry problems, is I consider this a solve for X geometry problem. In a solve for X geometry problem, you have to know the geometric relation between the things. If you don't know the geometric relation between the things, it's probably a good idea just to cash it in and skip the problem, and don't frustrate yourself and don't waste any time on it. Sorry to say, but that's it. And I counted geometry. I think there are about 90 geometric relations you need to know in geometry. You learn them slowly over 10 months. You learn 9 geometric relations a year. But if you don't know the geometric relation, there's really not a whole lot you can do in this problem. But the geometric relations come out of similar triangles, don't they?
Okay. Now it's critical. Okay, I'm going to talk about what's critical, but
go ahead.
This geometric similarity relation or ratio relation, is a consequence of this line and this line being parallel.
Ooh, we forgot to say that. Sorry about that.
That these two lines being parallel is what forces this proportion to be true.
Now
I'm a bit disappointed that they didn't, since it's so critical, that they didn't write it in English. Instead, they use these arrows.
Right, these silly arrows. Yeah. Now, this relationship comes out of similar triangles.
Yes.
If you don't use this is the quick way of writing it. But if you do it through similar triangles, little triangle 1 is similar to big triangle 2.
Yeah.
Right? So then you could write similar relationships. 4.2 is to n plus 4.2 as 2.9 is to 2.9 plus 5.8. And you would then
Yeah.
get a answer for n. It doesn't look like these would give the same answer, do they?
Well, let's work on it. First of all, let's turn both of these over,
Oh, you're right. Sorry.
and I'll write it out.
You
N
do it.
plus
Go ahead.
4.2,
Yeah.
which is, say
Yeah.
distance A.
The big thing. The big side.
I'll
Yeah.
call it A.
Fine.
Is to big A.
Is to the little.
Yeah, this is 4.2.
Yeah.
As the corresponding side of the big triangle, which is 2 and 9/10 plus 2, is to the
No. 2 and 9/10
to
plus
the
5.8.
what 5 point. I'm sorry.
5.8. Yeah.
5.8
That would be the big
to
thing.
the small one, which is 2.9.
Right. 2.9.
Now, what it helps to see is that when you break these up to add the fractions, what you get is n divided by 4 and 2/10
Right.
plus
1.
4 and 2/10 divided by 4 and 2/10,
Which is 1.
equals 2 and 9/10 divided by 2 and 9/10. Plus what is it, 5.8 divided by
5.8. Wow.
divided by 4.2. And as Joel pointed out.
No, divided by 2.9.
Yeah, okay.
Seth, divided by 2.9. 5.8 divided by 2.9. What's going on?
Yeah, well, I make a mistake.
That's a
2.9. 2.9.
2.9.
Okay.
Right, yeah.
And then these two things are 1, but in any case they're equal.
Yeah.
So you could cancel them out,
Wow.
and you get this. This relationship.
Wow.
This relationship here is equivalent to this relationship here.
I've never done that.
I think
That's really cool.
I think that this property of this property of similar triangles, delimited by parallel lines, I think it's a good thing to just to remember and remember and use for problems that it fits. Use this ratio relation.
So now,
even though use it, remember and memorize it, even though it's derivable and provable from the definitional proportions characteristic of similar triangles.
So, Seth, can I erase basically everything we wrote and go over the geometric relation that we're talking about?
Yeah, go over erase everything we wrote.
People. I live in the Bronx in New York City. Seth went to college in New York City. Went to Cooper Union, a great school. So we're very knowledgeable about Broadway. Broadway is and I'm sure most people have heard of Broadway in New York City. I call this theorem the Broadway theorem because I have to put some intuitive names to these geometric relations. I call this the Broadway theorem. You have I hate red. Let's do blue. Okay, you have parallel lines. Okay. Now this is Broadway because Broadway is not perpendicular to the streets in Manhattan. And then you have another street here. Okay, I call this all these lines are parallel. This is why I call the Broadway theorem. If you have A, B, C, D, E, and F, basically all of these little sections are all proportional to each other. You would say A is to B.
Yeah,
as
I'm
D
going
is
to make
E,
it bigger.
right. You got basically pick any of these. Pick anything on this side. It's proportional to the corresponding sides on the other
and
side.
make a bigger one. Make a bigger one here.
A plus B is to C, as D plus E is to F.
Make one down here, a big one. A, B, C, and call this X.
Fine.
And D, E, F, and call this Y.
That's right. So then here, look at this. And let's call, just for fun, let's call this whole distance 23, okay? And let's call this whole distance, I don't know, 19, okay? So then you can even say A is to 23 as D is to 19. You can take any little section on one side and it's proportional to the corresponding sections on the other side. I call this I personally call this the Broadway theorem. And it's
A is to 23 as D is to 19.
19,
that's
right. Any section you want. Just pull any section out you want and make it
that's a good idea. Yeah.
And I call it the Broadway theorem. Oh,
okay.
Seth, you're frozen. Excellent. Not good. Oh, no. Seth's face is frozen, but his voice is not. I hope he comes back because we need him for Throwback Thursday today. There you are.
Well, there's some other things I wanted to say about this problem.
Of course.
Okay, here we go.
Go ahead.
So, when I first saw the problem, here is what I imagined. I wondered if the data given on the left-hand side of the diagram was relevant to the problem.
Yeah.
Which would lead me to wonder, the problem. So here's what I imagined. I noticed that they gave numbers where this distance is equal to this distance, both of them 6 4/10, and this distance is equal to this distance, equal to 6. So I wondered, what relevance might that have to the two lines on the right? So here is what I imagined. Instead of this point being here, I imagined, what if that point were over here? Like that.
Yeah.
It could be just as well. Well, if having moved the point from above to below to the right, it's clear. I gave an example of the same geometric configuration in which the distance here, was small. These distances were small compared with these distances, which were big. Right? Okay. And so whether these two numbers being equal is given in the diagram, but the diagram could just as well been a diagram where these two numbers were not equal.
Not true. Believe it or not, Seth, as you were thinking, I realized that we made a mistake. We made a big mistake in our assumption.
Really?
We still got the right answer. Let's go back for a second. Seth before asked me, does this mean these are parallel? And I said, of course they mean they're parallel. I was wrong. These don't mean they're parallel. These mean that these lines go on forever. We made a mistake. Congratulations, Seth.
Really?
Yeah. Guess what? This is critical to the problem. This is critical to the problem because this tells you the lines are parallel. This doesn't tell you the lines are parallel. This is not a parallel line thing. I misled my brother. This only tells you these infinite lines. You need this. You need this because this tells you the lines are parallel. You need to see this, and then you deduce the lines are parallel.
Well, yeah, and it's an axiom in Euclidean geometry.
Yeah.
That two lines that are distinct and do not meet. That is a different concept from going on forever. They could go, the lines in Euclidean geometry, every line goes on forever.
Seth.
It's what you meant and should have said to instruct our audience in careful mathematics is that two lines might never might never meet. Two lines that are different, distinct lines, might never meet, which, in terms of going on forever, is a redundant statement that as you go on each line, no matter how far you go, forever, you will never find a meeting place.
So.
That is simply the same concept as they will never meet. Now, the principle of Euclidean geometry, and I'm saying Euclidean geometry because in modern mathematics, beginning in the 19th century, we know that there are systems of geometry for which many of the theorems of Euclidean geometry are true, in which the axiom is different, for which there is a concept of parallel lines. And in those geometries, sometimes parallel lines do meet.
Seth, stop all this stuff.
And sometimes parallel lines will meet in multiple places.
Someone, come on, forget all that.
So I object to distinguishing at the level of SAT questions, distinguishing between two lines that never meet versus two lines that are parallel. They are the same thing.
Okay, stop. This is geometry. You're going on a ridiculous tangent. The point is.
So you said I made a mistake, so I object.
Oh, okay, fine. I made the mistake where we assume that these lines were parallel. We cannot assume these lines are parallel. We have to use the green circle thing to look at it and say, oh, if 6.4 equals 6.4 and if 6.0 is 6.0, then we can deduce the lines are parallel. And then we can use parallel lines to do what we just did.
Is that true?
Oh, absolutely. A pinky bet. You want to see? Let's look at the answer. Pinky bet. Pinky bet. Don't you see what's going on here? Though that 6.0 and 6.4 are crucial to the problem.
Oh.
Yeah. Hey, Kat.
Oh.
Yeah, that's what's going on.
Oh, I see. Okay. I withdraw my objection.
Oh, okay. Thanks, Seth. No, but seriously.
I withdraw. Okay, so
let's get to the point. The point is that we still get
whenever. So I see. Yeah, I withdraw my objection completely.
Yeah. And when you were talking, I realized that was going on. That's what was going on.
Oh, that whenever.
Yeah. It's crucial.
Okay, so whenever. Yeah, we have that.
The other thing to do is, come on, if the lines aren't parallel, you can't do the stupid problem, right?
Yeah, right. Okay. Yeah. Okay. So, okay. My interpretation of the figure was that those arrows told us that the two lines were
Yeah,
parallel.
that was my interpretation of the figure also. In fact, I told Seth that's what they meant, and I was wrong.
Yeah. Okay.
Yeah.
So what they could have done to make the exact, so they could have made the problem harder. Here's a way they could have made the problem harder. First, omit the arrows.
Yeah. Okay. Yeah.
Second, draw the lines so that the in the drawing they are not parallel.
Okay.
And third, warn the students that the figure is not drawn to scale.
Right. But still have the 6.4 and the 6.0.
But still have.
Right.
Still have.
Right.
Still have those two
right.
Similar triangles.
Right. Yeah.
Where
So talking about
where
drawing the problem like this.
Where the the traversal in the top traversal bisects each line.
Right. Very good.
Oh yeah.
Okay, so anyway, I'm dying to see what they say. Okay?
Okay.
So let's see. So let's do this. Okay, so I guess we need to clear all our beautiful drawings. Okay, we need to do this, and we need
this is a hard problem.
Yeah, so maybe we should go back to the easier questions. But okay, then.
Okay, so let's see how they explain it.
Okay, here we go. First of all, do you remember the answer? It was 8.4, right? I think so.
Yeah.
Now we have to do little fireworks. Check answer. Fireworks. Yes, fireworks. Okay, here we go.
Let's see their explanation. Yeah, they say the upper line bisects the sides.
This tells us the lines are parallel. Yeah. So we misread the problem, mostly me, but we still got the right answer.
Yeah.
It happens a lot, actually.
Yeah.
Okay, and then
so again, the way they drew the problem to scale, and they put in a conventional notation. That many people interpret as saying that the lines are parallel.
Oh,
so that
they wrote the proportion differently than we did. They wrote the proportion different from the way I draw the Broadway theorem.
Yeah.
See what they did? They did the theorem. By the way, the Broadway theorem can also be written that way too. They wrote it. I don't like this way. They did 4.2 as to 2.9 as n is to 5.8. I prefer 4.2 is to n is to 4.2.
You silly.
As 5.8 is to 2.9. Sorry, it's so thick. I'm sorry.
Well, I think we should be aware that that equivalence, that if none of these quantities are zero, A is to C is
The bottom line is there's a personal choice here. Some people prefer to think of the proportion this way. I personally like to go section to section, as opposed to doing these two, as to doing it the orange way, which is this 4.2 is to 2.9. Okay, everyone.
Well, I would say here that rather instead of saying do according to your preference.
Yeah.
Yeah, I'd say it's wiser to be equally familiar with all of the possible ways a ratio can be expressed.
Right.
And treat them equally in terms of preference, and then pick an expression that fits the problem most efficiently.
Yeah, but that's also called not being human. We all have preferences, right? You're talking about being so incredibly objective, which isn't ideal. But come on.
Well, we should aspire to
We
ideals.
should aspire to ideals. We should aspire to
Yes.
ideals. Yes. But let me just say,
Yeah.
I always do it. I always drew the Broadway theorem this way. Okay. So when I do similar triangles, I do this side is to this side as this side is to this side, as opposed to the other way of doing it. But I know you could do it another way as well. When you cross multiply, you get the same answers. But Seth's right. You should know that there are two ways to set up the ratio, and that you should recognize that maybe in one problem, one way works better than another. So
yeah,
in this way, the way I set it up works better because it's without a calculator, it's actually easier. They do this thing cross multiplying, which okay.
Yeah.
So we think we're done with this.
Yeah.
Okay, today's Throwback Thursday, which means you go back to an SAT from maybe 25 years ago, from 1997, where it was more of a reasoning test. I think I've got a doozy question today. So the test post 2016 has reflected more what you learn in school, as opposed to being a genius and having a high IQ and reasoning. So let's go back to what a question would have felt like 20 years ago. So I need to stop the share. I need to get rid of this. No, I need to bring up a picture. I need to start the share. Here it is, and here we go. Here's our here's our SAT Throwback Thursday question of the week. Seth, do you see it? Do you see the question?
Yeah, I see it. Yeah.
Okay, so the screen's a little screwed up, but that's what happens on Throwback Thursday. Okay, here we go. This is from an official SAT practice book. This is not from a made-up. This is from an official book. Okay. So as you read it, we'll read it, and then we'll come back to it. And come back, pause, come back. A certain scale for weighing food registers weights only above 6 pounds. A person who wants to know the weight of one package each of chicken, beef, and turkey weighed every possible pair of these packages and got the following results. Whoa. Chicken and beef, 7 pounds. Chicken and turkey, 8 pounds. Beef and turkey, 9 pounds. What's the weight of a package of turkey? Something tells me you could do this through brute force with 2 equations, 3 equations, 3 unknowns. But something also tells me there's a trick. So I think it's worth investing a few seconds to decide if there's a trick in doing this, as opposed to doing a full-blown 3 equation, 3 unknown problem. Seth.
Okay, I think of a trick.
You can think of a trick where you don't have to do full-blown 3 equation, 3 unknown? Okay, go for it.
Yeah, here's a trick.
Go for it.
Here we go.
Or a pattern or something.
Yeah, here's a trick. This is a trick, not a pattern.
Go ahead.
Okay, here it is. Here we go. Let me do annotation.
Go ahead.
And drawing squiggles. Okay, here we go.
Ahead.
This is a real trick. Here we go.
Can't wait.
7 plus 8 plus 9 equals 2. Okay, let's use variables C and B.
C, B, T, obviously.
Turkey, beef, chicken, beef, and turkey.
Right.
The weights of the chicken plus the beef plus the turkey.
Got it.
Okay?
Got it.
And that equals, let's actually calculate it. 7 and 16 plus 8 is 24.
Right. 15
equals
plus 9
2 C plus B plus T.
So those add up to 12.
Therefore, 12
right.
equals C plus B plus T.
Right.
Now, what do we need to know? The turkey?
This is so smart. Oh, my God.
Okay, turkey. You want to eliminate C plus B.
Right. Oh, my God.
So we write C plus B.
Wow, this guy's
and we
smart.
know that C plus B equals 7.
Oh,
subtract and get 5.
Wow.
That's a trick.
So
that is a trick.
This is what the SAT back before 2016 was testing. Who can see that fast? Wow.
Yeah.
You are a smart guy.
Well, and this trick is employed many times over in combinatorics, and that's my specialty in mathematics. So it's something I'm very familiar with.
Yeah, but okay, fine. So what suggestions do you have for a person in high school? Well, this doesn't matter because they don't do this anymore on the SAT, right? So what advice would you have given someone 25 years ago who doesn't have experience in combinatorics to figure this out, other than doing full equations for three
loves
equations,
mathematics.
No, I mean, wow. I mean, to do the full equation, full.
Well, doing the three equations and three. Okay, my advice here is that if it doesn't come to you,
right,
just do the three equations and three unknowns. It's not that bad.
Right. Okay.
Do the three equations and three unknowns, keeping in mind that the goal is to eliminate B and C.
Right.
Okay, great. Now,
wait, but
let's actually do that.
Wait, but you could
let's actually
something.
do that.
Wait, but look, you could see a pattern if you're a little smart. You could just add these together. C plus B plus 2T is equal to 17. C plus B is 7. 7 plus 2T is equal to 17. 2T is equal to 10. T is equal to 5.
Exactly.
Look at that. So if you do,
well,
if you're not
when you write down, so the moral of the story is yes. If you don't see it, from your experience, actually start the routine methods, and then think.
Right.
The goal is to eliminate B and C.
Right.
And then notice that C plus B can be eliminated in one step.
Right. Wow, look at that. Wow, so it does work.
Now I think of an even faster way. After seeing these three equations, now we take the top equation and I'm going to put a circle plus next to the top equation and two minuses next to the next two equations. Okay. So you subtract from the top equation, you subtract both the bottom and the second.
Yeah.
So what happens is the C's are eliminated, the B's are eliminated, and right away you get 2T equals 7 plus 8. Oh, sorry. Equals 7 minus 8 minus minus 9. So does this make sense?
No, it doesn't.
Oh, no. Okay, it's minus 2T. There we go. So subtract the second equation and the third equation, and then what you get is minus 2T's. Minus 2T's equals 7 minus 8 minus 9.
So just...
It's another approach.
It's another approach, but
I think it's just as efficient as your approach. No, it's a little bit prone. It's prone to assign mistakes, so perhaps your way is better.
My way is better. Of course, my way is bigger. Of course, my way is bigger. It's a no-brainer. My way is better. No way is better. My way is better because you always want to stay away from negative signs and subtraction.
Not me. Negatives are great.
Oh, come on. Yeah, but
I'm a negative person.
You're not as negative as you think you are. Okay. Huh. I don't think so. So, okay. So, wow. So that means, one thing, you could be pretty sure about, even on the modern SATs, although we did see a full-blown 2-equation, 2-unknown problem, is that if you're stuck on a test that's basically a reasoning test and you're faced to solving 3 equations, 3 unknowns, the chances are there's a pattern to it, and they want you to try to see a pattern before doing full-blown 3-equation, 3 unknowns. So, okay. Although, the SAT is going digital starting in January 2024, and we did 16 practice questions. One of those practice questions was a full-blown two-equation, two-and-oh problem where you had to use elimination and actually do it slowly and carefully. So watch out for that. And if you're going to take the test after January 2024, be sure to know what's on the test, because the content may have changed, and we will do our part to try to figure this out as well, to figure out how the content is changing and advise you accordingly, give you our advice. But you should, I don't know what's going on here, but you should, Zoom is going crazy, but you should you do your own market research and do your own research as to what's going to change on the SAT once it goes fully digital. Okay, wow, Seth. So in practice, very few people are going to see the way you did it, because you have the experience. But hopefully, other people will see that if you write it out like the way I did it, you can see a cute little pattern. So look for patterns.
But even if you don't, if you write it out the way Joel started, and then do it systematically, eliminating C first and then B. It's not so bad.
It's not that bad, but there are going to be some negative signs in there.
Yeah.
So, yeah. Okay, everyone.
If you don't like the negative signs, you could eliminate with to avoid the negative signs. What you could do is take the equation with T and keep that a positive equation, and then subtract the equation with the 7.
Right.
And then subtract the equation with the 9.
Right. Yeah.
Yeah.
And I don't
So I see what's good.
Okay. So I guess that's it, right? We're done with Throwback Thursday. I hope everyone, long day today, 37 minutes. Sorry about that, but hopefully you got something out of it. If not, let us know how we could try to do things. You just
wasted 37 minutes of your life watching us stumble.
I suspect there are very few people who
stumble and make mistakes in explaining SAT questions.
What did you say? What did you say about making mistakes?
Stumble and make mistakes like we did with how do you know the lines are parallel?
That's right. Well, we did figure it out, but in the end, it didn't really make a difference anyway. Okay, so have a great day. Like us, dislike us. Please give us comments how we can improve what we do, and hopefully you're getting something out of this thing. Okay, see you later, everyone. Have a good day. Bye-bye.